Majority element. Have you ever stared at an array and wondered which value silently dominates the room? Majority element is a Pattern Mastery 100 essential and a favorite warm-up at Fong screens. Mastering it proves you can turn raw iteration into sharp insight with O1 space. Today we'll crush it using the basic framework and the legendary Boyer-Moore voting trick. Fast, elegant, unforgettable. Breakdown. We're given an integer array and guaranteed there's a majority element, a value that appears more than n/2 times. Our task: return that element. Because a strict majority exists, it must be the final winner if we pair off different elements until one remains. Assess. A hash map count would work in ON time but ON space. We can do better. Boyer-Moore voting runs in ON time and O1 space by tracking a running candidate and a count. When we see the same value, we vote +1. A different value votes -1. Whenever the count drops to 0, we switch candidates. With a guaranteed majority, the final candidate is the answer. Structure. Plan. Initialize candidate equals none, count equals 0. Iterate through the array. If count equals 0, set candidate to the current number. If current equals candidate, increment count, otherwise decrement. At the end, return candidate. If the problem didn't guarantee a majority, we'd re-verify by counting, but here it's guaranteed. Approach. Hashmap count. Time complexity. ON. This line defines the solution class. In Java, all our logic must live inside a class, so this simply acts as the container. This is the main method. It takes an integer array and returns the element that appears more than half the time in the array. Here we create a hash map called M. This map will store each number as a key and how many times it appears as the value. Think of it like a tally sheet where we count occurrences. This loop goes through every number in the array one by one. For each number, we update its count in the map. This line increases the count for the current number n. If the number hasn't been seen before, get_default gives us 0. Otherwise, it gives the existing count. Then we add 1 and store it back. Pause. This is the counting step. Right after updating the count, we check if this number appears more than half the time in the array. If it does, we immediately return it, because the majority element is guaranteed to be unique. This early return makes the solution efficient. This closes the loop after all numbers have been processed or once the majority element is found. This line acts as a safety fallback. In a guaranteed majority scenario it won't be reached, but it keeps the method complete. This closes the method. And this closes the class. Final wrap-up. And that's how this algorithm works. It first counts each number as it scans the array, then immediately returns the one that crosses the majority threshold. Efficient, simple, and elegant. Test case check. Majority element, hash map counting. Let's test our function using this input. 3, 2, 3. This array represents a list of numbers, and our goal is to find the majority element, the value that appears more than half the time. Here's why the solution works. We build a running count for each number using a hash map. As soon as any number's count becomes greater than n/2, we return it immediately, because by definition, that number must be the majority. And that's exactly what our program outputs. 3. It matches the expected majority element perfectly. Wrap up. So, our implementation is correct. The algorithm successfully identifies the element that appears more than half the time. Simple, efficient, and accurate. Approach. Boyer-Moore voting algorithm. Time complexity. ON. This line defines the solution class. It's the container that holds our majority element logic. Here we define the majority element method. It takes an array of numbers and returns the element that appears more than half the time. This line initializes two variables. Cand will store our current candidate for the majority element, and C is a counter that tracks how strong that candidate is. This loop goes through each number in the array one by one. Since we scan the array exactly once, this contributes to an ON time complexity. If the counter drops to 0, we choose the current number as the new candidate. You can think of this as saying, we don't have a strong candidate right now, so let's start fresh. This line updates the counter. If the current number matches the candidate, we increase the count. If it doesn't, we decrease the count. This is like pairing off different numbers against each other and canceling them out. This closes the loop. By the end of the scan, the true majority element survives all cancellations. Finally, we return the candidate. Because a majority element is guaranteed to exist, this candidate is the correct answer. This closes the method. And this final brace closes the class. Final wrap-up. And that's how this algorithm works. It first initializes a counter and candidate, then scans the array canceling out opposing values until the majority element remains. Efficient, simple, and elegant. Test case check. Majority element, Boyer-Moore voting algorithm. Let's test our function using this input. 2, 2, 1, 1, 1, 2, 2. These numbers represent a list where one value appears more than half the time. Our job is to identify that majority element. Here's why the Boyer-Moore algorithm works. We keep a running candidate and a count. When the count drops to 0, we switch the candidate to the current number. Then, for each element, we add to the count if it matches the candidate or subtract if it doesn't. And that's exactly what our program outputs, too. It matches the expected value perfectly, proving the voting algorithm worked as intended. Wrap up. So, our implementation is correct. The algorithm successfully narrows down the majority element using constant space and a single pass, efficient, accurate, and reliable. Majority element. Let's do a recap. Ever face a problem where one number seems to quietly take over the whole array? Majority element is that test of insight, a simple setup that exposes whether you can think beyond counting and find patterns in balance and dominance. Breakdown recap. Conceptually, we're finding the element that appears more than half the time in an array. Because that majority always outnumbers the rest, even if we cancel out every pair of different elements, the true majority will still remain in the end. Assess recap. We compared two main approaches, using a hash map for frequency counting versus the Boyer-Moore voting algorithm. Both run in ON time, but Boyer-Moore uses just O1 space, elegant, efficient, and the clear interview favorite. It tracks a candidate and a count, adjusting as elements vote for or against it. Structure recap. We structured it around one simple rule. When the count hits 0, pick a new candidate. If the current number matches it, increase the count, otherwise, decrease it. By the end, the guaranteed majority remains as the final candidate, no second pass needed. Implement recap. We ran the logic step by step in LeetCode, and it executed perfectly. No errors, no extra space, just clean, consistent majority detection. Check recap. All test cases passed. The algorithm correctly identified the majority element across different arrays, confirming that our approach worked exactly as expected. Closing insight. The takeaway? Majority element teaches one of the most elegant uses of mathematical balance in algorithms. Once you understand how to cancel out competing values, you'll start spotting similar patterns in many optimization and voting problems, fast, clean, and interview-proven.